It's my pleasure to introduce Jie Ma from two university USTC and Tsinghua. And we actually know his recent results on Ramsey. We had two talks about it, about non-diagonal Ramsey. But today he'll talk about something else, since I asked him to talk about something else, about supersaturation for color critical graphs and beyond. So please, dear, it's a pleasure to have you.
So thank you, Andre, for the invitation and for the introduction. I'm very happy to have this opportunity to give a talk, so online to all of you. This is about a supersaturation problem, and actually it is based on two joint work. One with the first guy, Longtu Yuan, and he's a professor now at Shanghai Normal University. Actually, it's not Shanghai. Sorry, it's Eastern Normal University, but it's located in Shanghai. The second paper is joint with another three authors here. Especially, I want to point out like Yongtao Li. Actually, you know his relation with your postdoc, right? Yeah. Okay. So I think he probably is
Yeah, I know. And I
sitting in the
think
audience right now.
he's in the
Yeah.
audience, yeah.
Yeah. Okay. So in case you have question, you can also ask him, you know. Okay, joking. So here's my overview. My talk will consists of four parts. First is the background, and then the results of the first paper, then the result of second paper, and then have a short closing. So actually, we're going to talking about the two different supersaturation. The first one is the standard one. So the condition is we are given the number of the edges in a graph which exceed the current threshold, and therefore the graph must have lots and lots of copies of some fixed graph you are interested in. It's more like the classical setting. The second one is called the spectral supersaturation. So we are no more given the number of edges, but instead we are giving some condition on the spectral radius. And under this spectral radius condition, you want to say, okay, then the graph must have contain many copies. But although those two seems to be different, but as we're gonna see later, both projects basically heavily relies on this stability method. But of course, each paper, require different analysis for the stability. I'm gonna tell you more later. Okay, here's the two papers I mentioned. The first one is published last year, and second one is we just posted online a couple months ago. So here's some headlines of each paper. The first one, the main thing is basically to study some wider family of graphs which beyond color critical. I hope everyone know what is color critical graph. Color critical graph is a rich family which including all the clicks, all the cycles, and so on. And the supersaturation for color critical graph has been settled many years ago. But so the theme of this paper is basically to extend this into a larger family. And the larger means actually we call this family called the color K critical, which including graphs like Peterson graph and so on. And there, then we also study some general problem which proposed by Zhu Mubai. His question is kind of nature. So he's asking if a given graph F has very good stable property, then is that the case that you can always expect that the supersaturation problem for this graph is basically extension results of his Turing numbers. And we actually found some counterexamples to say this nature problem is not always the case. Okay? For the second paper, we're interested in the spectral supersaturation. So we are given lower bounds of the spectral radius, and I can tell you what is the natural lower bound. And then we want to do the usual thing. We want to estimate the number of copies of the given graph. Okay. Okay. Now in this slide, I want to emphasize the main functions we are interested in. The first one. So we are given a non-bipartite graph f. For bipartite f, of course, people also study the supersaturation problem of it. But that is more like close to the theory of Sidorenko or Erdős-Simonovic. So it's not the scope we're going to consider today. So F is for now it's an arbitrary unbipartite graph, and we define his Turing number Ex and F to be the maximum number of edges in an F-free graph. And then we want to know if we are adding more edges to this threshold, then as a definition of this Turing function, as long as you have exn f plus 1 edges, the host graph must contain at least one copy of f. Okay, so the question is, what is the minimum number you are always guaranteed that you can find this many copy of f? So we are interested in if you're adding 1, adding 2, adding q many edges. Okay, and today's talk basically focus on the linear range of q. So oftentimes you're gonna see that q actually is linearly in n. Okay, and but we also know that actually people are also interested in say when q is in the order of say n squared, right? But that's something different. Okay.
Yeah, sorry. Can I ask you a question? Also, I guess people can ask. Can people interrupt you during the talk? Is it fine?
Sure.
Right.
Yeah.
So
Yeah.
I wanted to ask, when you say linear range, you mean at most linear range, meaning anything at most linear or exactly linear?
So Q will be a parameter,
Mm-hmm.
which is like between 1 and the Cn.
Okay.
Yeah. Any number in this range. Yeah.
And when we are talking about copies, do we mean the actual copies or the number of homomorphism or something like that? Not.
So copy means like not induced, like everything.
Okay.
So it's actually a good question. So the talk is not like structure. So we're not particularly interested in the induced copy of f. But if you're talking about the induced copy of f, then usually the problem is called the inducibility. Okay. So here, copy of f means okay. So the formally speaking, the copy of f means the number of collection of edges where those edges will induce a copy of f. Okay.
On the same set of vertices, like if a graph is 10 vertices,
Yeah.
and you can still see one copy, or you can see like 100 copies potentially.
You can see
right?
100 copies. Yeah. Yeah. If f has 10 verses, and in a set of 10 verses, you're gonna counting multiple times. It's like but it's actually not an issue, because it's not a problem, because yeah, so copy of f means the number of collection of edges which induce a copy of f. Is it clear?
Yeah, thank you.
I think it's clear.
Yeah. Okay. Thanks. That's actually very important. So h function is the main function we are interested in, but there is another sort of natural candidate for this h function called a t function. So t function is the minimum number of copy of f which obtained an extremal graph by adding q edges. Okay, For example, if it's a triangle, then you know the extreme family, the extreme graph for the triangle is the balanced bipart, complete bipart graph. So then a natural candidate is like you're gonna adding more edges into this copy. So you're gonna adding Q copies, right? Although you are allowed to freely place your Q edges at any place you want. Okay. But anyhow, by looking at this particular family subfamily, there is a minimal number of copies of F. Okay, so we're gonna denote this to be TF. So according to this, you're gonna easily see this inequality that the F function is always at most a T function, right? Because for the F function, you're looking at a larger family of graphs. So when you take a minimal, this is smaller than T. Okay. But in this business, we are very interested in to trying to understand when this inequality becomes an equation. Okay, that is when this extreme family, extreme graph for supersaturation of F contains the extreme graph of the Turing function. Okay, that's basically one of the main things in both papers. Okay. And on top of this, we're going to introduce another function called the C function. Okay, CNF is equal to TF N1. So that is the number of copies that you read from your extreme graph of F by adding one edge. Okay, by adding one edge. So from the definition, you also say TFNQ is at least Q times CNF. I didn't write this in inequality, but it's kind of also important for us. So T is bigger than or equal to Q times C. Is this clear?
Yeah, it is clear, yeah.
Okay, good. Okay. Okay, having introduced those functions, now we look at a little bit of history. So the problem actually begin with the classical results of Turan, the Turan theorem. And then in 1955, I think Erdős and Rademacher started initial this supersaturation problem. So they first look at triangle. If you are giving like Q many edges more than the Turan function of triangle, then how many copy of triangle you're gonna get? And then I think this is now becomes a classic exercise in a graph theory problem. You want to know what is the minimum number of triangle in a graph with n squared over 4 plus 1 edges. Okay, the answer is half n, right? And half n come from the Turing graph. And then people study, people including Loas and Simonovich, they study cliques. And there are actually lots of papers. And in this direction, right now, we know much more. In particular, this maybe 10 years ago, Christy Hile solved a conjecture of Loas. Basically, whenever Q is so for that you look at a slightly different range where Q actually is anything like a C times n squared and C can be anything. So you are interested in basically the asymptotic problem of the supersaturation. And Chris Carroll solved it completely, which answers the conjecture of solve the conjecture of Loas. And then in 2010, Drew Mubai he had this breakthrough. The main ingredients is that he finds like this graph remove lemma can play certain role, and then he used it to basically enrich the theory from cliques to color corrected graphs. Okay. And then 7 years later, Pikuko and Jie Ma basically refined Drew's results. And they're gonna see later. Okay, so first of all, so we understand like if f is a clique, then those two functions are equal. Not only when q is in linearly n, but actually in quadratic in n as well. Okay. But again, today we're gonna consider q is a number between 1 and Cn, for example. Okay. Now let me introduce you the formally what is a color critical graph. Okay, a graph is color critical means that there is an edge. When you remove this edge, the chromatic number will go down by 1. Okay, so therefore, for example, cliques they are all color critical. All the cycles are color critical, and there's some other graph.
Sorry, can I ask
Yeah.
you? So you mean if deleting any edge lowers
1, no 1.
just one?
One. Yeah. If you delete any edge, it's also called it's
Mm-hmm.
also a weird known like it's a weird studied
Mm-hmm.
family of graph, right? But usually it's studied by structural graph theory, I think.
Mm-hmm. Okay.
Yeah.
So just one edge is okay.
Yeah.
Yeah, I
Yeah.
understand why. Okay.
Yeah. That's very important. Okay. But it's also good because actually we're looking at a larger family than what you just asked, right? So yeah. Okay. Now Simonovich he basically solved the Turan numbers for any color critical graph. Okay. And his result is to say like the Turan graph is the unique extremal graph for such F. Okay. And his proof is kind of remarkable because that's sort of the first application of the stability method. Uh-huh. Um, and then okay, there are many intermediate progress I skip here, but let's directly jump to the result of Mumbai, the sort of modern result. So he proved that for any color critical graph F, if you looking at Q, which is the linear range, so Q is between 1 and some small constant delta times n. Delta is constant only depending on F, but you can regard this as a arbitrary small constant. Okay. Now in this range, he proved that the H function, again that's the main function we're interested in. That means the minimum number of copy of F in an n vertex graph with exactly Q plus EXNF many edges. Okay, and he proved that this number must be bigger than Q times CNF. Okay, and actually we have to mention that this bond is asymptotically tight, and it's precisely tight for big family. For example, when F is odd whale, when F is odd whale, then it's color critical, and basically for odd whale you see it's an equation. Okay, so at least it's asymptotically tight. Okay, here's the result. And then in 2017, Pikuko and Jie Ma basically refined his argument. They adopt a more advanced analysis of stability, and they prove that for the same range of Q, those two functions are equal. Okay, so this one will be much actually it's at least imply this one because earlier we say for the T function T is at least Q times Cn, right? So this is a direct corollary of the theorem 3. Okay, so that's very good.
Yeah, just a small question here. So you said asymptotically tight. So Q times CNF is asymptotically for at least for this range is 1 plus little of 1 this TF, right?
Exactly. Yes.
Mm-hmm.
Yes.
Okay.
So for this, it's basically 1 minus lambda of n times TF for this one.
Mhm.
Yeah. And T is also nature upbound, so this is asymptotically tight. Okay. The reason is actually it's easy to see because why this is tight. Uh, I think the easiest way to say this is like if when you look at the T function, the midterm is Q times Cn. The midterm is contributed by looking at the contribution of one edge. Yeah, when you're adding many edges to your Turan function, a Turan graph, for example, right? Then you know some copy of f is created by one new edge, right? Some of them may be created by two new edge, right? But the main contribution will come from those one edge. Yeah.
And at which point this thing breaks? Like, how big should be the number of added edges when this is no longer true, kind of?
You mean
Like
when
quadratic or this asymptotic equality that we just discussed? The TF is equal to QC F.
you mean for color critical?
Yeah, for example, for color critical, or maybe, yeah, I guess.
If so, later you're gonna see we have a
Mhm.
result basically tell us that if f is not color critical, or if f is sign no a little bit weird graph, then even this is not true.
Mm-hmm.
Even this
Mm-hmm.
is not true. Okay, so like actually h is strictly less than q times c. Um, but if you want to only restrict to color critical graph, um, I think the answer is not yet known. Like
Mm-hmm.
only for very special f, we can answer your question. If
Mm-hmm. Mm-hmm.
beyond this range, we don't know much.
Okay.
Um,
Okay.
yeah,
And
But
also, can I ask one more question? For
sure.
example, yeah, if we compare the functions h and c, for instance, put q equals 1, and can we find some graph f such that h is significantly smaller than t?
Very good question. Okay, I postpone this later because that's exactly one of our question. Uh, the answer is yes. You do uh, are able to find such a graph. Um, in our paper, this first paper, we are able to show you example when Q is full. Okay, but I think Yongtao Li and another student, a postdoc in Shandong University, they are able to construct such graph when Q is one. If I'm not like completely forgotten their results. I think they are able to answer your question.
Yeah, thank you. Yeah, it's very interesting question, I guess.
Yeah, it's interesting. Yeah, but I think it's one, right? Yongtao, you are able to show when Q is one, is this is
Oh, yes. We have constructed a graph in the case Q is equal to 1, and we
yeah,
don't write the paper completely.
yeah. But you should write it down because people are interesting. Yeah. Okay. Thanks. Yeah. So uh, again, there are graph when Q is one, and this function is strictly less than C. Okay. Okay. Let's move on. Um, So here is a definition which generalize the color critical definition. So color critical definitions is basically say there is an edge. When you remove it, it's lower your chromatic number. Okay. And here we say F is color critical graph, meaning that there is a choice of KH. When you remove it, you lower your chromatic number. But I mean, this is at least very natural to say you can define such graph. But then you find out like this is not enough. You have to actually a little bit modify this inspiration a little bit. So the right definition to put this is also the right. This is a definition provided by Simonovich. So we need to say that the KH you removed, they are called induced KH. Okay, meaning when you look at the edge set of those KHs, it's this induced subgraph only has KH. Okay, and then their second condition is to say remove any k minus 1 vertices were not enough. Remove any k minus 1 vertices will not lower the Kurymatic number. Okay.
K minus 1 vertices?
Yes, vertices.
K edges there.
K edges.
So we remove kind of an induced subgraph on K edges. Yeah.
Yeah.
But K minus 1 vertices is not enough.
It's not enough. Yes.
Okay.
And now combining those two conditions, you're gonna say that the K edges actually must be an induced K matching. If the suitable K edge is not a K matching, then you can find the K minus 1 vertices which dominate the K edges, right? But then this will be contradicted to the second one. Yeah. So really it's about like matching of size K. Okay. Now a couple of examples. This family of course contains the original definition of color critical graph. It's color critical becomes color 1 critical, right? And it also contains, for example, the disjoint union of cliques. It contains Knizia graph K2T. And we know K5T is the Peterson graph. So Peterson graph is, I think, is color 3 critical. Okay. And there are some other family which I didn't include here. Okay. So here I want to just maybe give you the impression that when we say F is color K critical, basically you can view this family as this graph as like there is a matching of size K. When you remove this matching, it's reduced his Kurymatic number. That's like the main primary impression for this family. Okay.
So can for the Knezzer graph, so KT2, so 2 element subsets and a T element set, right? So this is what you mean.
Yeah, two subsets of size 2 will become your vertices.
Yeah. And what is the parameter K there?
What's the parameter K? When T is 5, I think K is 3. Peterson graph has 3. Yeah, matching of size 3.
Okay.
For other T, I'm afraid to provide you answer because
okay. I was just thinking, is there an easy way to see like what we are removing? But immediately I don't.
Yeah.
Okay.
Yeah. I forgot. Yeah, it's a long time ago. I guess probably like a T plus 1 choose 2, I guess. But
or maybe wouldn't we just look at this kind of subset of size 4 choose 2, we remove the matching that is forms there, like actually maybe it's 3 everywhere, and then kind of in the coloring of the Knezzer graph on this subset of 4 elements of the original ground set, you use only 1 color instead of 2 as you usually use, something like that. So maybe it's 3 always.
Let me look at the paper.
But yeah, I think it should be, my feeling is that it should be 3. I just at least removing 3 edges with the reason induced matching on with 3 edges, and removing them decreases chromatic number.
Yeah, right.
Yeah.
In the case for other TTs, at least 6, the Canessa graph KT2 is color 3 critical. Yeah, you're right.
So yeah, my feeling is you take 4, choose 2, like, and then in 4, choose 2, this graph has 3
Yeah, you're right.
edges.
It's always color 3 critical.
Good.
For n at least 5. For t at
Okay.
least 5. Now the answer is always 3 as 3.
Great,
Yeah.
great. Thank you.
Yeah. Okay, next slide. So here I want to introduce you the extremal graph for color K critical graph. Okay, this actually define. This is a theory. This is a theorem of sim knowledge. So his to run extremal graph is the following. So you have a click of size k minus 1 on top, and that's your x. And then you have for the remaining verses, it form R-balanced subsets. Okay, and then you put all around the edges. This is a two-round graph, and you connect between any x and those vi. Okay, and then you can argue this particular graph contains no copy of f if f is color critical graph. And then you say adding any edge will create at least one copy of it. Okay, and his result, which generalize his well-known color critical graph as basically is for color critical graph. Is this clear?
Yeah.
For this graph. Yeah. I mean, because assuming the coordinate number f is r minus 1, right? And here you only have k minus 1 versus. So it's not enough to put your graph here. Okay, I leave this exercise to you. Now let's okay. So here is the conjecture of Zhu Mubai. So basically, here we ask if f has very good stability results and it's non-bipartite, then is that is always true? Okay, but the answer is no. At least, actually, we know now for every given integer, the answer is no. Okay. Now I just say one more slide before we jumping into the results we proved. So two papers. First one we discuss edge supersaturation. Another we discuss spectral supersaturation. And both papers basically are interested in basically if f equals we are interested in the extremal graph of supersaturation actually is coming from the extremal graph of two-round function. Okay, and there are a couple of like different those two problems are kind of sharing the same theme, but they have different behaviors, and we're gonna discuss it. Okay. Now I'm entering the second part of my talk, discussion this beyond color critical graphs. The first result is a counterexample to Zhu's conjecture. So in particular, we prove the following statement. So for any q, at least 4. For any and q now is a fixed integer. Okay, q is a million, 10, whatever. For any such q, we can find a stable non-bipartite f such that his h function is no more than 1 minus delta times q times c. And delta is a positive constant here. Okay, so in particular, we know the h function is no more than q times c, which is at most t. So this is a consequence of the result. And as Yongtao pointed out, they have recently a new construction which can lower the value of q from 4 down to 1. Actually, they show me once what is the graph that I've got. Okay. So it's interesting to tell us that the stability itself is not enough to determine the minimizer of the supersaturation problem, right? Because his motivation is to say like the extreme graph for supersaturation always grow from the extreme graph for Turan. Okay, but this is not the case. Even the F has very good stability, but it's not the case.
And here, a quick question also. So this delta Fn bound on Q, like intuitively, I would imagine that it should be even easier to get counterexamples for larger Q, or I'm wrong.
You are right. You are right. Yes. So actually, like back then, we're really fighting for the minimal Q we are able to get. I think we at the beginning we get like 10, and then slowly we lower to 4. But the 4 is the limit we have. Yeah. Yeah.
What does it mean that F is a stable graph?
Okay, here's the formal definition of the stable. So F is stable, meaning the Turan number of F has a unique extreme graph, and around that, basically that's it. Like F is stable, meaning his Turan function has exactly one extreme graph. Yeah, actually, what he conjecture is for any hypergraph. For hypergraph, I have to add one more condition. But since for graphs we have the area seminology, so that condition is automatically hold in the graph case. So for graph, you just need to think about like this stable means EX and F has unique only one extreme graph. That's enough. Okay. Now this is the counterexample we have. It's actually easy. So you have a matching of size k here. Okay, k is at least 2. You have a matching of size k, and then you have P4 union a matching of size k minus 2. So the union means disjoint union. Okay, and then you join them. So you put all edges between those two sets of vertices. Okay, P4 means the 4 vertex path. So you have k independent edge on the left, and you have k minus 1 independent edge plus this P4 here. And then you join the two paths. Okay, and then you see this graph has coordinate number 4. And moreover, we're able to show this is a stable color k critical graph. Yeah, because this matching of size k will serve as a matching that I emphasized back then in the definition of the color k critical graph. Okay.
And on the other side, you also have a matching of size k, right? So P4 is it's kind of it's two matchings, but in one matching you add one edge, kind of.
Exactly.
Right?
Yes, and this is also important. Yeah. Okay, so the smallest case it work for the calculation is when k is 2. So this is the graph. Okay, and for this the smallest q works for the calculation is when q is 4. Okay. Okay, now I mean, although we say this is wrong, right? But I have to point out to you what is the host graph make this wrong. We have to compare with the extreme graph, which is earlier I defined it's called H and R, right? That's, you remember, you have k minus 1 click on the top, and you have a Turan graph lower, right? And then you want add q. You want to add q edges. So you add, and q is small. It says q is 4. So you add 4 more edges to your extreme graph, but you want to compare with some others, yeah, and you want hopefully to say that for the some others it has fewer copy of f, right? And here we created such a graph. It's called H star. Okay, H star is you also have k minus 1 vertices on the top, but this is the independent set instead of the clique. Yeah. So here you're gonna missing k minus 1 choose 2 edges. Okay, and for the other parts is the same. Here you have to run, and between them you make it complete. But you need to add, you want to add more edges, right? You want the way you adding edges is to put as those edges as a star. So and the star are gonna have size q plus k choose too many edges. Yeah. It's not quite. And then you have to do some, a small perturbation. That is, you want to delete the k minus 1 edges between this independent set and the center of the star. Okay, so the difference is here you have an independent set and you have a big star, but you also delete the edges between the center and this eye. Okay. And once you have those two graphs, it's just direct to calculate how many copies each of them contains. Okay, and you want to compare those two numbers. And you find this one has fewer copy of than this one. Okay, that's it. Let me see here what I said. Yeah, okay, here's the proof. So I have defined H star, and I think the main proof will be to analyze what are the types of copy of F in H star. Okay, and there are several types of copies of F. But the point is that the main term is contributed by a single edge. Yeah, so the main term will be you just use a single edge here together with the R partite graph. If we're using more than 2 edges from the star, then it will contribute to this maximum number, and this is small compared to the contribution from 1 edge. Okay, so you don't need to worry about those. Okay, and then basically the deletion of those particular k minus 1 edges will play a role, because you don't have this particular edges between the star and this, so it limited you the number of embedding. Like missing those k minus 1 edges will limit you the embedding. So you're actually gonna have fewer copy of them at this edge. Yeah, that's the at least the intuition. For the real proof, you have to calculate the numbers, so it's not interesting, I think.
And here the constants are like this. So basically 2 versus 5, like 2.5, right?
Yes.
Over 2.
In the end, you basically compare like 2k with this, 5k over 2.
And it looks like it will work. Wait. No. So it like beyond linear number of edges, it kind of breaks down because there are too many edges in the star or something. Oh, wait.
No, that's the same example. Also, it works for QX4, and it also works for anything up.
But even above linear, no.
Above linear, no, because
No,
once
no.
you're above linear, this term becomes dominating, right?
Ah, right,
Yeah.
right. So it's yeah.
So the two edges contribute like q squared times this, and the single edges contribute like q times n to the 3k minus 1. Yeah. That's why we
So
need,
yeah. So this is why we need the small constant times n. It's like always this phenomenon.
exactly. Yeah, exactly. Let's simplify your picture. Yeah.
Okay.
Yeah, thank you. That's for the negative result. Here I want to discuss the positive result. So the positive thing is basically for a particular subfamily of color K critical graph, you do have the equation between H and T. And here we call this subfamily, call it like a divisible color critical graph. It's a bit delicate, so I didn't include this definition. But the important thing is when K is 1 and 2, any color air critical graph when air is 1 and 2, they are admissible. For all of those kinetic graph KT2, they are admissible. And for disjoint cliques, they are also admissible. Yeah. So basically, I would say like for those graph, indeed, this is still equation. Yeah. The particular case I want to discuss is the Peterson graph, K52. And that's the numerical result for this Peterson graph, where you can actually calculate what is the copy of Peterson graph when you're adding one more edge. It's roughly n to the 6 divided by 32. Okay. The host graph. I probably want to skip it because it's very special. So yeah, I want to skip this. For the admissible, okay. Here is the formal definition for the admissible. So graph is admissible, meaning that so so we're talking about any embedding type. Yeah. So let's talk about a kinetic graph. So kinetic graph KT2 has chromatic number T minus 2. So and then you look at basically any partition of his vertex set into T minus 2 paths. Okay, and I will call this any partition. We're gonna call it like embedding type. Okay. So then this T minus 2 paths will give you T minus 2 subgraph, right? I call it F0, F1 up to F T minus 3. Okay. And then the definition of admissible basically is you want to verify certain inequality in terms of those subgraphs. Okay. And that's the inequality we're gonna compare. The reason is when you're down to the counting, so that you have to, I mean, it's everything is delicate, right? So you have to find some systematic way to counting the copy of F in your graph, right? You have to given some pattern to it. So one way to view it is so you view this as like an ordered subject, right? So you partition your vertex set into certain parts, and say usually also T minus 2 parts. I mean I'm talking about the host graph, and then you look at each of those T minus 2 subgraph in your host graph, and basically you want to say that each of them contains here the corresponding Fi. Um, but there are many ways you can basically resemble your copy of F, right? And there's a number of ways, so many. So you are not able to handle them all of them. So we have to have given some sort of precondition, which can you simplify your counting. Yeah. And this precondition at least work for our calculation. Our proof is those two. Yeah. You have to given some precondition in terms of any embedding type of your kinetic graph, then you can simplify your calculation a little bit. Okay, I hope I at least explain the difficulty. So
here two questions. So these conditions, the right hand, so it doesn't look too strong because the right hand side, or this 3 and 4 are something. So it depends on the graph, right? So this
the graph.
It's kind of this K critical, something like that, right?
Exactly. So because any kinetic graph K T2 is 3 critical, right? So that's why this number is 3, and this number is 4. If in general this becomes K and this becomes K plus 1. Yeah.
And it's always about the embedding of these graphs into the to-run kind of graph, right? Into this H graph.
Exactly. Yeah. You always want to adopt that perspective. Yeah. I mean, so it is the easiest way to explain this is like those two conditions are not natural, they are artificial, but that's the one we need in our calculation. Like that's the thing. Yeah.
To control kind of the different types of embeddings.
Decrease the number of embeddings you want to discuss. Yeah.
Okay.
Yeah. Otherwise, it's not easy to like count how many copy of F you have. Okay. Probably skip this. This is still about the Peterson graph. Yeah, it's Peterson graph. Let me skip all of them. Okay. Okay, now I discussed the third result in the first paper. This one tells us if we're talking about the threshold of Q for which H and T function are equal. This result tells you that the threshold can be anything. So in particular, the threshold can be anything of the form n to the power 1 minus 1 of s for any s. Yeah. So for clicks, for example, the threshold is oh no, click is not the example. So anyhow, so our results basically tell us that like in general, the threshold can be very delicate, like can be anything of this form. So when Q is less than n to the 1 minus 1 s, this is equal. When Q is bigger than this is really less. Okay, and for each s you give me, I can provide you a copy of F.
But maybe even non-integer are possible, or it's unclear.
Oh, for us it has to be integer, but maybe maybe
Okay.
that I don't know. Yeah, because our example is actually also some particular color K critical graph, and for that it gives us this form. Yeah. Yeah, here this picture is basically again telling us this threshold can be anything of this form. Okay. The proof. All of those three results basically using the same. I mean, if we are not for not talking about not for the contact examples. Contact example is just you directly compare the two graph. But if we want to establish some positive results, then basically we adopt this routine procedures. So we apply the remove lemma and stability first to basically this will tell us that your host graph, I mean the minimal. When we say the host graph, you can assume it's the extreme graph for the supersaturation that has the minimum number of copy of F, right? And then basically using those two things, you can already have a rough structure of your host graph. It will be very close to your extreme graph for 2RAM. Okay. And then basically you adopt this classical stability, that is, you define what is the bad edge, you define what is the missing edge, and you do very refined arguments like discussion, how many copy of F containing one edge, how many copy of F containing a missing edge, and you do such things. And then after some manipulation of this inequalities, you are able to show the missing edges. There's zero missing edge. So basically, your graph is a super graph of your extreme graph for 2RAM, and then basically you're done. Okay, so the routing is basically this.
And here for the removal, it's the usual removal lemma, right? So actually at that point we're like at little of n squared scale or something like that.
Yes.
So
yes.
Mm-hmm.
And then for this we have to contribute. I mean, the credit is due to Jie Ma. Like he's the first guy to realize like you can in this business you can involve remove lemma.
Mm-hmm.
And you can basically have this new extreme structure.
And for this step, we actually, so this is the first step, we don't need the linearity, right? So it's again, for Q being like little O of n squared, probably it should work also, right?
Yes, you're right. Yes, exactly. When Q is in the range of little of n squared, it should work. Yes, very good. But mainly we need this linearly in n because we have to compare like Q square, right? Like
This one edge, the linear for one edge copies, right? So for this,
yeah. You want the linear because you want to say a single edge dominate the other type.
Mm-hmm.
Okay, let's move on. Now we discuss the second paper for the spectral supersaturation. For this type of results, so we are giving a graph whose spectral radius is at most something, and then you want to say under this condition, your host graph has many copy of your given graph. Yeah. In some sense, this setting is stronger than the normal setting. The reason is the spectral radius that is the largest eigenvalue of the adjacency matrix of your graph. We know that the lambda is at least 2 times the number of edges of n, right? So if you are given the number of edges, like if EG has a lower bound, then this lower bound automatically becomes a lower bound of lambda, right? Therefore, if you have a theorem which can tell you a theorem can tell you that given a lower bound of lambda, you get like certain copy of f. This is actually a stronger result than the counterpart, right? You see what I mean?
Yeah. That's
so
because
in
of this
some sense,
inequality. Yeah, it gives like lower bound on E gives lower bound on lambda. So
yeah. So the spectral version actually in some sense is stronger than the edge version, but it's not quite because Those two problems are different, like different in many sense. Okay. And there's a problem asked by Ning and Zhang. So they basically want to know if there is a spectral version of the mobile result, if there is some refined statement of for this edge color critical graph. Okay. Our main purpose of this paper is basically to answer this question. Yes, you can establish a reasonable spectral version of mobile result, and you can do this for all a color critical graph. Yeah. Okay, now let's go a little bit further. The question is, what is the natural extension of Zhu-Mobile's theorem, right? Remember, for the edges, for the Claxis setting, you are given many edges, and that's your condition, natural condition. Okay. Now your question becomes, what is the natural lower bound you want to impose on your lambda? Yeah, because if I'm adding, say, two edges, but adding two edges to a Turing graph, but a different resulting graph may have different lambda, right? Like in terms of edge counting, it's always +2. It's constant. But now, if in terms of the spectral radius, because you have many graphs, and those graphs result in different lambda, right? So what is the natural lower bound you want to impose? That's indeed a pragmatic problem. So there are three natural candidates. I'm going to explain you later why they're natural. The first one is you have a R-pattern Turing graph, and then now you are adding some edges, Q edges, and you are adding those Q edges as a matching of size Q, and you add it in the larger part. Okay, you add the Q matching in that. For this resulting graph, I'm gonna call it Y. This is the graph Y graph. Now, if you want to, instead of a matching of size Q, you want to adding a star of size Q, then we call this the T graph. Okay. Now you also can put your star in the smallest part of the graph, and this graph is called the error graph. Okay. And we have a characterization. This tells us that the Y graph has the smallest spectral radius, and the error graph has the maximum spectral radius.
One thing, yeah, I think that maybe we should mention is that for the extremal problem, at least, because I mean, now I was thinking about it, I realized that it's okay, but maybe it's not clear that for the extremal problem, the answers will still be the same, because the graph is like, I mean, at least, let's say for the triangle, the graph is complete bipartite, so it's a regular graph, and thus you have equality between this lambda and the E over N, right? Meaning, because a priori it's not even clear what should be the answer to the extremal problem, like when you don't want to see the triangles, let's say, or some kind of graphs, and because you are already talking about supersaturation, but I guess so. Maybe you can comment on that, because at least I'm understanding it only for the case of the triangle. But in general, right? So it's, you see what I mean, right?
But for that, I mean, the answer, I mean, at least if you adding edges into your to-run graph, right? Or adding edges to your extreme graph for the to-run. There are multiple ways to do that, but it's much easier to analyze like what is the optimal way, right?
Yeah. But the problem is, so here it's specific for the So for the moment we are just discussing the potential extremal families without.
Because we are no more talking about the number of edges, right? Number of edges is not our condition.
Yeah.
We're talking about like spectral radius. What is the lambda?
Yeah.
I mean,
Yeah.
this is really like a problem, right? Because what is the natural condition we want to impose? Like, what is the lambda? Because
Yes. I understand. So we still, so strictly speaking, we don't, at this moment, we don't even know whether any of these graphs, maybe there is a graph with bigger spectral radius without even one copy of our graph or something. We're just building some graphs and hoping that they will be maybe extremal. And okay.
So when I'm talking about like a spectral supersaturation, I'm talking about I'm gonna replace the condition on the number of edges by a lower bound of the spectral radius, right? That's it.
Yes.
Yeah. So we have to argue for that. Like, what is the natural condition? And at least those graphs are the natural candidates. When we're looking at the aiding thing, right? Oh, here I forgot. Define this family. So we defined the capital TNRQ to be the family obtained from the R part of the to-run graph by adding Q edges. Okay. So this will be the natural candidate anyway. But inside of it, like which one have the maximum spectral radius, which one has the smallest spectral radius, it's not clear. Okay, so we have to. We prove this. Like inside of this family, Y has the smallest lambda, L has the largest lambda. Okay, and T is somewhere in between. That's one thing. And another thing is like actually is the difference between those three graphs is not much. Like basically each edge it will have a difference no more than like 2 over n. Yeah. So the difference actually is no more than q over n. Okay. Quantitatively speaking. Yeah, okay. So for the moment, we know that for the minimizer is to adding a matching, the maximizer is adding a star.
Excuse me, can I ask a question?
Sure.
So if we're trying to add some edges with the matching number equals 1, so in the case q equals 3, we compare the triangle and the star, yeah?
Yeah.
And the added triangle, in this case, we have
you're just asking very special case, and the result actually is like when q is 3, it's different from other cases. Yeah, as we stated here, like when q is 3, actually the maximizer is the triangle here.
Yeah, so there is some intuition because you consider the k starting from 4, yeah, in the previous result, and now the q equal 3 is a special case, and so there is some intuition about it, maybe.
The intuition is the spectral radius is basically is you can rephrase it as the counting of number of walks. And when you adding a matching, it's basically creating the fewest short walk. Yeah. When you adding a star, basically it gives you the maximum number of short walk. So this is basically, you know, at least give us a intuition why this is a maximizer, this is a minimizer. Okay. Actually, okay. But to our result, actually, this is not important because I think Yongtao helped me to modify this slides. I hope I understand what he's talking about here. But we have two main results. The first result is say when lambda is at most, sorry, when lambda is at least the minimal of everything. And we know, because we know the minimal is a y function, so here we put a y, right? When lambda g is at least the minimal of the graph from the family, from this family, then we can prove that G has at least Q times C many copy of F. But this only works when Q is no more than root n. Because we know that when Q is bigger than root n, there is a counterexample. So when you post the minimal as your condition, the optimal thing is Q has to stop at the root n range. Now, if someone imposes the maximum as a condition, so maximum is the error function. So if you say your lambda is at least the maximum, then of course your lambda is better, right? It's bigger, so you expect something, better result. And indeed, in this case, the Q can be anything up to linearly n. Like if you impose the minimal condition, Q has to be no more than root n. But if you impose the maximum condition, it becomes linearly n. Not only that, you actually also can gain something. Like earlier, you say the result is to say it at most it's Q times C, right? But in this case, actually, you can gain one edge. You get Q plus 1 times C. But this like I think this already implies people the case when people study triangle. Like there's some before our results, there are only one sort of paper falling in this the live study is when people study triangle. Yeah. And I think so they study basically when Q is 0. But our results basically is much general, and they also cover that particular case.
So here, so here these lambdas from the L family and from the T family, they're kind of interlacing. So meaning it's lambda of T nrq, then lambda of L nrq, then lambda of T nrq plus 1, lambda of L nrq plus 1. So are they, because right, so it's like we can also apply theorem from the previous slide for Q plus 1 and also get this Q plus 1 bound. I just wonder whether these sequences of lambdas, they interlace kind
of. Interlacing?
Meaning, so this, so if you look at this, so you have these two families. If you vary Q from 1 to something, you have the lambdas of the L family, and you have the lambdas of the T family. So for each value of Q. And I'm wondering if they're interlacing in the sense that first, the smallest one is TNR0, then LNR0, then TNR1, LNR1, etc., etc.
That sounds like a very we don't know that. Like it's if it's true, it will be like it's required even more refined analysis when you calculate those spectral radius. Um, but under some certain under some suitable condition, I think at least we can compare, basically one thing when I'm talking about the counter example, you're gonna see such a
Mm-hmm.
yeah. So the short answer is we don't know that. Yeah, and
Okay.
I think
Okay.
that will be interesting.
Interesting. So you kind of get bounds which are similar, right? So for this TNRQ plus 1, you get almost the same bound as for LNRQ, but you are not completely sure if like the first one is
Yeah.
bigger than. Mhm.
No.
Okay. Interesting.
Yeah. Okay, thanks. So the big message here I want to send is when lambda is bigger than the maximizer, then the range of Q can be linearly in. If the condition is the minimizer, then the range of Q can only be up to root n, and this is tight, we know. Okay, and there is an intermediate range where you replace this by the t. Yeah, because we're talking about three graph, right? The y function, the y graph, L graph, and the t graph. And in the t graph, we can also like also set up a result which works for linearly in Q. I mean, this is sort of like an application. The main purpose of to include this is this condition is particularly conjectured by Li, Lu, and Penn in a paper. So actually, this is we include this as an application of our main results. Okay. So here's another picture. So Y has the smallest lambda. So T it has an intermediate lambda, and the L has a maximum lambda, right? So if your condition is imposed on Y, then basically like this condition is weak, and therefore you get a little bit worse ratio. When you going up, then your condition is becoming is stronger. So but then you get a stronger threshold. Yeah. Um, Now here's another page of summarization. So summary. So I think I skip. Yeah. Okay. Let's talk about the proof. In the proof, there are two main ingredients. One ingredients we call it like the spectral increment estimate. That is so you give me a graph which is very close to the Turing graph with alpha bad edge and some missing edges. Yeah, and the number of missing edges and the number of bad edges are constant. Yeah, and you give me this graph, and I'm able to estimate. I'm able to provide a rough estimation on the spectral radius. That's basically the first result we need. The second one is basically a stability. So you give me a graph and you know his lambda is big, but the number of copy in your G is small. Then in this case, we're able to say the graph must be very close to Turing graph. It's like stability. Because all you need is just replace a lambda by the number of edge, right? If you replace lambda by the number of edges, this is the typical, stability statement. Okay. Those are the precise statements. So G is obtained from the complete upper graph by adding alpha 1 class edge. So alpha 1 edges will be usually we call it bad edges in the stability analysis. And then you also delete alpha 2 many crossing edges. So now you have alpha 2 many missing edges. Now, if we assume alpha 1 and alpha 2 are constant, and the partition is basically balanced partition, then you're gonna know the lambda of G is basically not far from the lambda of K. And lambda K is the two-rank graph. So basically this is like a constant. We assume this is constant. And we are able to estimate like the difference between those two. This is controlled by constant over n. Which you can basically regret, like if you're adding a class edge, then the spatial radius will increase by n over 2. If you delete one, it will delete another. It will go down by 2 over n. So here, that's why you get like 2 over n times alpha 1 minus alpha 2. Okay. The second one is the stability. So you are giving this condition, and you say because you basically you look at the minimal, you look at the extreme graph with minimal number of copy. So you're gonna have a condition on the number of copy, which is no more than q plus epsilon times n. And under those two conditions, you already can guarantee that your graph is close to the two-rank graph. So this conclusion actually becomes the condition of the previous result.
So this epsilon here is really like some small, very small constant, smaller than 1, right?
Epsilon actually can be taken as anything less than 1. For example, in many cases we choose epsilon to be 0.5, I think.
And how do you get this? So this, you said that this statement follows from the statement. No, not from the statement on the previous, or from the statement on the previous slide.
Oh no, I'm saying the conclusion of this one. The conclusion of this one becomes the condition of this one, right?
Yeah. Okay. So will you comment on how you get this stability for the spectral, like the statement from the next slide?
Right. So, but if you're talking about the proof of this one,
yeah.
The proof of this one is not very, difficult. Basically, it's root from it's root. It's item from the classic Erdős-Simonovich stability. Yeah. It's
So here small numbers. What is the order of small in this statement? Like linear in n or little o of n squared?
You mean q?
I mean this that G can be obtained from some complete tripartite graph by adding only a small number of basic non-two-rank graph edges. So this small here is, what is the order?
It's linearly in q. Small means linearly in q, if I'm not like mistaken.
Yeah. So really small. Okay.
Yeah, linearly in q. Yeah. Okay, now let's very briefly talking about the proof. So when I say the y threshold, I mean we are given the condition lambda g is at least lambda of y. And under this condition, we want to say our graph must contain many copy of f, right? So using this as the condition, and the target is to show that the ng is at least q times c. Of course, we already assume our graph is minimal, in the sense like it minimizes the number of copy of f, and then n is no more than n of y, which is no more than q plus little 1 times c. Yeah, so like sort of automatically you get this the upper bound of this. Okay. Then once we have this, you will see like the condition for this second ingredient hold, right? Then we can apply this. Then you know already the graph G is very close to some complete upper graph by some edit of a linearly in Q many edges. So then you define that lambda 1, lambda 2 is linearly in Q. And then you can use the first result, right? The first result, like saying that is with this setting, the lambda of G is not far from the lambda of K. Yeah. Then I've applied some very refined estimation. We're able to say that in this case, the only case can be is alpha 1 is Q and alpha 2 is 0. And the paths are balanced. At this point, you already finished the proof because you know your graph belongs to this family, and therefore your graph must have this. Yeah. So the key point is a proof proof of those two ingredients, like the two earlier results. Okay, now here's the example. Earlier I say if for this condition root n is the right answer, the reason is when you look at click, right? And you will find this graph TNR Q minus 1 is bigger than his special radius is bigger than the special radius of YNRQ, but this graph only have Q minus 1 times C many edges. So this is sort of, Andre, it's basically partially answering your question.
I see that this kind of things happen at reasonable values of Q. Yeah. Mm-hmm.
Right. It's a little bit like alternating. But only when Q is bigger than 2 times root n, this becomes true. Yeah. Okay, and the proof of the error graph and for the T graph, they're basically routine. I mean, no, this required even more refined analysis in terms of this special radius. And we have to, I think we have to define several operation. It's more complicated, but basically the approach is the same. We're trying to use the two results we established earlier. I think I skipped it. Yeah, okay. So here's the short summary. So for the two papers, so each of the paper relies on the stability method, but the way we use it is different. The first paper, the key argument is more like combinatorial, but the second paper is more like analytic because you want to by putting or deleting edges, you want to see how this change lambda, right? So therefore you have to basically you looking the argument is you look at eigenvector and eigenvalue estimation, sort of that as I want to end with some open problems. Oh, here's another summarization, so I skip it. The open problem is I want to mention three. So the first one is you want to for the admittable family. So you want to so basically it's you want to ask for the method we have, what is the maximum family for that to hold? Okay. The second question is, so for the spectral supersaturation, we mainly discuss color critical graph. But beyond color critical graph, can we also, establish a systematic study for that? For example, can you also study color critical graph? Can you study Peterson graph? Okay. Another question is, can we extend this to hypergraph? Because in Mubai's approach, he has a sequence of 3 papers, and in his last 2 papers, basically he discussed hypergraph. But for example, for spectral supersaturation, I mean, in theory, we also can discuss hypergraph. But then the problem is to define what is the right spectral definition for the hypergraph. You have multiple definition for eigenvalues of hypergraph. I think we can do several quite many similar things, and I'm not sure like if it's worth it. Okay, so with that, I finished my talk. Thank you.
Thanks a lot, Jie. So, questions from the audience? Of course, we asked a lot of questions on the way.
Yeah, maybe one more question. So, in the first article, you compare, for example, in the case Q equals 4, you find some graph such that H is less than Q minus some delta. Q minus some delta, yeah?
Yeah.
4 minus some delta times T. So can you find some graphs that says that we have more significantly gap? For example, T over 2 or something like that, such that H will be less than T over
Yeah, I see the question. My guess is no, you cannot find the like significantly smaller. You mean we're talking about the order of the magnitude, right? I don't think you can find.
Yeah, do you have some lower bound? H, for example, is more than T times something, maybe.
H is T times something.
Like epsilon times T or something like that.
Yeah, maybe T over 2 or something.
I guess so. Yeah, I guess so.
But yeah, so this kind of is it's a bit in line with what I wanted to ask also, like more generally speaking. Yeah, for me to look interesting to ask the following kind of questions. That okay, we relax a little bit the type of supersaturation we want to get, in the sense that maybe we don't get exactly, well, as Yasha says, don't get exactly this H at least T, or H is equal to T, and maybe yeah, this is. So we relax this to some weaker condition, or maybe we relax the structural condition to a weaker condition, meaning that not necessarily we look at the class corresponding to T, but maybe, but something stronger still than the. Of course, we have this removal lemma and the Shimona, this kind of Shimonovitz or Mubaya approach with this. So we know, I guess, in any case that examples should be kind of similar to Turan graphs, but then there is something maybe in between, being like Little and squared, and maybe being exactly Turan graph. So relaxing these conditions, but then getting the results for the whole range, maybe kind of for a bigger class of graphs, something like that. So this people haven't looked much into it so far.
No.
Or
Yeah. So you are basically you will be satisfied if you know if Q and if H and T are of the same magnitude, right?
For
You will be
example,
happy
yeah.
for that.
Yeah,
And
yeah,
then
yeah.
you want to say you want to enlarge this range to
Yeah.
something like n to the 1 plus epsilon or even later over Q
Yeah.
squared.
Yeah, or enlarge the range of graphs that this works for them. The
Yeah.
types of graphs, yeah.
I don't
Mhm.
think. No. Okay. I think for H critical, people know it.
Mhm.
For H critical, people know it up to later over n squared.
Mhm.
Like in this paper, if
Mhm.
you they didn't like state in that way, but basically in this paper, I think answering your question, I think the answer is yes for H critical.
Mhm.
Yeah. So as long as H is in the same magnitude of T, then you can basically push your Q to later over square.
Okay.
Yeah. And then they have a second paper. They only study a very special graph called bow tie, like two triangles sharing one vertex.
Mhm.
For that graph, they can go all the way to like C times n squared.
Mhm.
And for that graph, they even know this, that H and T are equal.
Mhm.
But this is a single special graph.
Okay.
And after that, I don't think there's much study. Like, I mean, of course, we have this matching critical, our result, but our result is limited to the linear range, right? It's not,
Mhm.
yeah.
Yeah. Okay. Interesting.
About the color critical graphs, you got what do you think about the hypergraphs? The conjecture is also not true, or it may be true.
So for hypergraph, we have to talk about those hypergraph which we understand histogram behavior, right? If we don't understand histogram behavior, there's no way to even to state the result we are interested, right? So and for hypergraph, much less hypergraph we know exact Turan numbers. For example, we only know final plan, right? And the final plan is exactly the second paper of Zhu Mubai. So he set up a theory which worked for the three uniform final plan. I think that's his main motivation to make the conjecture. Like he see like it's true for graph for all color critical graph, and now it's also true for this final plan. Therefore, he would like to see like actually it works for all stable hypergraph. But it's not even true for all graphs. Yeah. And after that, I don't see much result about supersaturation of hypergraph. Yeah, the main reason is I think people are still developing the Turan type of result for hypergraph. And that's also difficult, still very difficult. So I think people not yet are ready to look at the hypergraph of supersaturation for hypergraphs.
Thank you.
Thanks a lot, Jie. I think I enjoyed the talk a lot. It was it was very interactive, very nice, I think. And
Thank you.
yeah, hope to see you maybe in August, but we'll
Yeah.
discuss this later. Okay.